Hello, everybody. So what we're going to be doing today is we're going to be going over the number bases and conversions lecture slides that are posted here in the week 7 page. So I will download those, which is happening now, maybe more than once, and we'll open them up. So these lecture slides here are going to be going over the basics of binary, octal, decimal, and hexadecimal conversions. And we've seen this a little bit, but this is to kind of prepare you to do the SciBooks exercises. So we'll just get right into it. So a number base, which can be called a radix, defines how numbers are represented. So the normal numbers that we use, of course, are base 10, right? We assume because we have 10 fingers that that's what people wanted. Now that's also called decimal, which you have to be careful that you're not confusing the word decimal like a decimal point with decimal that means base 10. So the word gets used in both places. Now, when you're using base 10, that means you have 10 possible symbols. So the 10 possible symbols you have for decimal are the digits 0 through 9, right? And so because 0 is one of them, it only goes up to 9, and we still get 10 possible digits. And in binary, we know binary means base 2, binary means base 2. That's going to use the digits 0 and 1. Again, the highest digit that we have is one less than the base. Um, so binary is base 2, uses digits 0 and 1. We need to know how to use octal, which is base 8. That makes sense, right? Octal 8, which is going to use the 0 through 7 digits. And then finally, we need to talk about hexadecimal, which is base 16, which uses the digits 0 through 9 and A through F. And that's just because if we're using base 16, that means we need 16 possible digits, just like, base 10 needs 10 possible digits, base 8 needs 8 possible digits, base 16 needs 16 possible digits. But we don't have 16 digits, right? Because we are naturally users of base 10. So I'm just opening up a place to type real quick. Make big and zooms in the way. Let's close this. So the digits that we use are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits so far. We need 6 more. So we use A, B, C, D, E, F. And so if you count those up, right, you have 10 to get up to here, and then you have 11, 12, 13, 14, 15, 16. 16 possible digits. And so they correspond to the numbers that they are, right? 0 is 0, 1 is 1, 2 is 2, 3 is 3, 4 is 4, 5 is 5, 6 is 6, 7 is 7, 8 is 8, 9 is 9. A. A is 10. A is 10. B is 12. I don't know why I said that. B is 11. C is 12. D is 13. E is 14. And F is 15. So the digits are 0 through 15 when you have base 16. But we don't have one single symbol that means, 14 or 15 or 11 or 12 or 10. So that's why we use these letters just as substitutes for them. All right. So those are the digits we use for hexadecimal. Now, when we're converting from base n, so that's just any other base that's not decimal, to decimal, then you essentially just want to think of every number as being multiplied by a power of whatever the base is. So just like we know, I'm going to go back over here. Just like we know that if somebody says like 783, right, that actually means 7 times 100 plus 8 times 10 plus 3 times 1, right? And we know that the 100, the 10, and the 1 are just the powers of 10, right? Well, you can do that exact same thing for any base just replacing the 1, the 10, and the 100 with whatever the powers of whatever that base are. So, for example, like let's say we had the exact same number, 783, but instead of being in base 10, like we had up there, what if it was in base, um, I was going to say base 6, but this can't be base 6, right? Because it uses digits of 7 and 8. So it's got to be at least base 9. So let's just say that this is base, let's just say it's base 16. Okay, let's just say this is a number in hexadecimal. And you might think like, well, wait, it's not hexadecimal because hexadecimal has A, B, C, D, E, F in it. Yes, but also no, right? Just because we can use A, B, C, D, E, F in, hexadecimal numbers doesn't mean every hexadecimal number has it, right? Like 783 didn't use any nines. Didn't mean that we weren't allowed to use nines. Same thing here. 783 doesn't use A, B, C, D, E, F, but the fact that we were allowed to, means it can still be a number in base 16. So what this would look like then is the exact same thing here. 7 times 100, uh, 8 times 10, 3 times 1, except we have to replace the 100, the 10, and the 1. And so the 1 is still 1. The 10 would have to be replaced by 16 to the first power, which is just 16. And the 100 would have to be replaced by 16 to the power 2, which I believe is 256. But there we go. This is what it would look like. So that's it. So that's why conversion in this manner is not that hard. So like if you wanted to know what 783 base 16 is in base 10, you just do this calculation where the 3 would be multiplied by 16 to the 0 power, 8 is multiplied by 16 to the 1 power, and 7 is multiplied by 16 to the 2 power, right? Because we can think of it this way. 3 times 16 to the 0, 8 times 16 to the 1, 7 times 16 to the 2. And you punch this into a calculator, which we can just jump over to like Wolfram Alpha or something and put that in. And we get, it's 1923. So that is 1923. That's what it would be in base 10. So 783 base 16 is actually 1923 in base 10. And so conversion that way to decimal is not that bad. So conversion from base, n to base 10 is not so bad. That's what you got to do. Also, there's a bunch of calculators that can help you out online if we, need that kind of help. So coming back over here, let's find our slides. This is just another example of that. So this one was base 6 to decimal. So we had 352 base 6. Notice that they listed it as a subscript here. We could have done that, except that I was typing in VS Code, so I don't have subscripts available, right? So that's why I just wrote base 16 in parentheses, which is what people do. But this is base 6. So for base 6, same thing. The 2 is in the ones digit, so that's going to be 2 times 6 to the 0. Then you have 5, 5 times 6 to the 1. And then you have 3, 3 times 6 to the 2, right? Exactly what we did with 16, but this time with 6. And if you multiplied those all out, then you're going to get a number 128, apparently. All right. Now, the other direction, which we may have talked about in one of our lab periods, was converting decimals to base n, which is the other direction. And so when you go the other direction from decimal to a particular base, that takes more effort. Okay. And so what you have to do is you have to do kind of repeated division. And I do the division in sort of a table. The table helps me. And maybe I don't know if I can do this. I just had an idea and it's a dumb idea. But oh, you know what I can do? I can pause the video and then I can come back after I know if I've got a dumb idea or a smart idea. Give me 1 second here. Although for you, it should be quick, right? Oh, come on, Zoom. All right, I'm pausing it. All right, I am back. So I don't know how good my idea was still, but here's what we're going to try to do. So let's say we wanted to convert the number 128 to base 6. And here a calculation is being shown where we are repeatedly dividing by 6, and we're keeping track of the quotient, and also we're being keeping track of the remainder, right? The 2, the 3, and the 3 are the remainders. Um, Now, what I do is come over here and we'll look at an example to convert 128 into base 6. And so what you do is you can make a little table that looks like this one, where we have number divided by n, and number mod n. So that's going to be the remainder right there. And into this table, what we do is we put um, the number that we are starting with here, so 128 goes in this first column. And then what we have to do is repeatedly divide it by the n here. So I'll grab a calculator, which I suppose we have, and we'll do it with this calculator. Although I don't see how we can do modular arithmetic, so we'll have to do it the old school method. So first thing we'll do is we'll take the 128 and we'll divide it by 6. So you go 128 divided by 6, and we get that that's 21 point something, right? So what you do is the number divided by n, you put the 21 there. And then you have to find the remainder. So this is where, it'd be nice to have something that could just easily calculate the remainder. Since I don't have it, I'll just have to calculate this myself. I'll basically have to do 128 minus 21 times 6. And so 6 is the base, 21 was what we just calculated for the quotient, and we get 2. So our remainder is 2. So we have 128 divided by 6 is 21 with the remainder 2. Then you go down to the next row, and in the next row, what we put is the number that's here moves down to here. So we get rid of that 128 and put a 21 there. And now we have to recalculate the other two columns. So we have 21 here, and then we need to do 21 divided by 6. Now, thankfully, 21 divided by 6 is pretty easy. 21 divided by 6 is going to be 3, right? Um, then we need the remainder. So 3 times 6 is, oh, wait. um, how many times does 6 go into 21? It is 18. Okay. I don't know how to brain fart. So 6 goes into 21 3 times. We get 18. And the remainder would also be 3, right? So after we do that, then again, the number that's here comes down to the next row. So I'll have to go put some of these in. And the 3 comes down here. And then we have to do what's 3 divided by 6. 3 divided by 6 is 0. And what would the remainder be? The remainder would be 3. And then the last thing would be you can try to take this 0 down here to the next row, but that's actually your indication that you're done. So when this becomes a 0, you're actually done. You should not finish filling out the row. And so when we do this, we get these numbers here, 2, 3, 3. And so what you do is you start at the bottom. So the bottom number is a 3. And so 128, which is base 10, is going to be what in base 6? Well, start from the bottom here. 3, 3, 2. 3, 3, 2 in base 6. Okay. And that's how you do the conversion. So you do it every time with a little table like this, and it works out okay. Now, the same calculation should be presented in the notes here, um, just without it being in a table, and we still get the 332 at the end. All right. And so that is converting from decimal to base n. Now, another thing that you might want to do is convert from binary to hexadecimal. And there's really a shortcut here. I don't know if the table's in here. Let me see. It is. And so the trick with hexadecimal is that I'll even put it here. Hexadecimal. So the thing about hexadecimal is that there's each digit is, from 0 up to F, right? Which we know is 15, right? So there's 16 digits. And if you think about binary numbers a little bit, what you'll remember is that if you need 16 possibilities, you would need a 4-bit number to describe uh, these digits from 0 up to F. So it would take 4 bits to describe those digits. And what would those be? Well, I'm not going to make the table here because it's tedious, but 0 is 000, right? Um, Maybe I'll do this. 0 is 000. 1 would be 0001, right? 2 could be 0010. 3 could be 0011. 4 could be 0100. 5 could be 0101. 6 is a 4 and a 2, so that's 0110. 7 is 0111. We finally get up to 8, which is 1000. And actually, they're going to start repeating here. So if I were to take these numbers and just paste them and go 8, 9, 10, 11, 12, 13, 14, 15, all I would have to change is the first digit in each of these to a 1, and this should be correct. So the point here is that these digits from 0 up to F each can be described with a 4-bit number, correct? Right, we see that? And that is what is right here. So this is just the same table that we just came up with. And so the thing about this is whenever you're trying to convert a number into hex, you just do it 4 bits at a time. So I'm just going to make up a silly example, right? So let's say example. And what are we doing? Why did this? Oh, what kind of example? Let's write the binary number. Gonna just separate those out by 4s. Actually, no, I won't. So here's a binary number with, I think we have, I don't know how many uh, digits. Hopefully it's divisible by 4. So we want to do that. So if we take this right here, and then we can just split it into 4. So you go like 1, 2, 3, 4. I'm just going to put an underscore to visually separate it. 1, 2, 3, 4, underscore to separate it, 4, underscore to separate it. Then this looks like 16-bit number here has 4 groups of 4 in it, right? And then what you do is you just take each of those 4 groups, 4 digits, and you convert them individually into a hexadecimal character. So this first one here, right, the one that's 0100, you just look up here for 0100. And so I find it right here, right? 0100 is a 4. So you say that first digit is a 4. And then the next digit is 1101. So you look for 1101. I find it right here. 1101 looks like it's D. So that is D. And then the next digit is 0111. 0111 is 7. So you go 7. Oops, 7. And then the last digit here is 1100. You find 1100. 1100 is C. C. So this binary number here is actually 4D7C. So binary to hexadecimal is actually really easy. You just group the numbers into groups of four, start on the at the one side, and you just convert them in groups of four directly using a table. Quite simple. Okay. So there'll be an example of that here. So this number was 10100101. And so we split it into two, 10100101, and then you look up each one. So the 1010 is A, and then the other one, 0101, is 5. So that is A5. Easy as that. Okay. Now you can do the same thing for octal and binary. Just octal, instead of having 16 possibilities, it only has 8 possibilities, and you just do them in groups of 3, essentially. So if you needed to convert a number from to octal, so let's say, example, convert, we need number with digits less than 8. So let's convert 372 in, let's say that's base 8, specifically to binary, base 2, right? What would that look like? Well, each digit here is going to be converted into 3 bits. So each digit is 3 bits, right? It was 4 when we were dealing with hexadecimal, but when we're dealing with octal, each one is 3 because there's only half as many um, octal digits. So we need one less bit. So each digit is 3 bits. So you convert them individually. So like the 3, what would it be as a 3-bit number? Well, 3 is just 2 and 1, right? So it would be 011 as like a binary number. And the 7 as a binary number is 111. And the 2 as a binary number would be 010, right? And so what does that mean? Put it all together, and it means that 372 base 8 is going to be, sorry, yeah, that's right, is going to be, and we just do it this way, 011111010 in base 2 binary. Okay, and you can do that the other way around. Going the other way around would be exactly the same as what we did for the hexadecimal, except that we only have eight digits to worry about instead of 16. All right, so that's going to be it for this video. You'll have to look at the next video if you want uh, me to go over the Zybooks exercises for this particular topic. All right, that's it for now. Talk to you guys later.